So this is actually one of the reasons why I stopped doing videos all about physics. It's because of the sorts of objections that I've had to field in the comments over the past. But I mean, yeah, this is just one thing that I had this morning. He was talking all about how I've been, or how my theory flies in the face of Kepler's laws and so on and so forth. It does not fly in the face of Kepler's laws at all. One of the objections he was raising in his comment was that it would that my theory would imply that for objects in free fall they decelerate, which clearly isn't the truth. So my theory must be wrong, right? Except that's not the truth at all. Since objects in free fall, all objects in orbit in stable orbits around the sun, which is what Kepler's laws applies to. They apply to objects in stable orbits. Those objects are in free fall, more or less. That's a roughly speaking good analogy for them. In much the same way that this, when I drop this, I just release it from my hand. This ashtray is in free fall around the Earth, and it eventually hits the Earth's surface because there's a force of attraction there. What I was talking about with Oumuamua is that that is not an object in free fall around the Earth. That's an object coming into our solar system with excess momentum, um, which slingshotted around the sun and decelerated on its approach to the sun. So, I mean, there's two explanations for this. Either there's something going on with gravity causing the object to decelerate, um, or it's aliens in a spaceship, right, and they're slowing down the spaceship so they can get a good look at our solar system, I guess. So, and that really does seem to be the two explanations. Either there's some unknown or mysterious facet of gravity, and gravity is really a very mysterious force still. It's something that's not completely understood by any stretch of the imagination. We still have big open problems in the study of gravity, such as the study of dark matter and dark energy and so on. Or that, yeah, it's aliens. So, I mean, I don't want to rule out aliens. I like the idea that aliens exist, but I just don't think it's very likely. That's all. And yeah, it's not a violation of Kepler's laws. For instance, if I throw this ashtray very very fast, my idea would predict if I was to throw it around the sun very fast or around the Earth very fast, my idea would predict that the excess momentum would be attenuated over time. So it would, as it's entering the gravitational field, there'd be electrical resistance from the electrons surrounding this ashtray, interacting with the electrons from Earth, and that mutual interaction creates a force of repulsion and would slow this down if it were moving fast enough, or too fast, I should say, for a stable orbit around an object. So when it comes to Oumuamua, Kepler's laws don't really apply, and I'm by no means stating that all objects in free fall would experience deceleration. I'm not talking about free fall at all. I'm talking about something that already has too much momentum to be in free fall, if you see what I mean. And then there were other objections in the comment. I'm actually going to look up the comment because it's quite eloquently written, in fairness to it. It was clearly a lot of thought went into it, so it's only fair, I think, that it deserves a sort of long-term explanation. So I've just got past the paragraph that was talking about Kepler's laws. When an extremely well corroborated law appears to be falsified in very specific instances, it rarely indicates new physics. I do know that, I'm sorry to say, thank you, but usually it means that the known laws of physics are not being completely applied, or some particular circumstance needs to be included in the modelling. Yeah, I know that, thank you. For example, Uranus's deviations from the orbit predicted by Newton's laws, given the known planets at the time, allowed Leverrier to accurately predict the existence, mass, and position of Neptune. Leverrier did not take the anomaly as falsification of Newton's otherwise well corroborated laws. There's a sign that the model of the solar system to which they were being applied was incomplete. Okay, there's a whole paragraph just on that, isn't it? Or does he say something more interesting at the end? Similarly, in this case, Oumuamua's anomalous trajectory could be explained if we include the forces created by outgassing and solar radiation pressure. Yeah, I knew I read that paragraph for that reason, isn't it? Yeah, like, it could be accounted for using radiation pressure. Well, how do electrons repel one another? You need to think about that. You need to think that electrons repel one another via exchanging photons. So, I mean, that's how the force of repulsion manifests. It's via this quantum field theoretic this quantum electrodynamic process of repulsion with photons being exchanged. So to say radiation pressure, that's tantamount almost to saying the same thing. I'm sure it does come down to radiation pressure. However, I'm asserting or stating that the medium through which the radiation is propagating is electromechanical, is electrodynamic in nature, it's composed of electrons. So, photons literally do move through space in these zigzags, and between each point on the zigzag is an electron. And that's why we have radiation pressure. And for some reason, light propagates through space in this way. You've got to imagine that the whole of space being filled with these particles, being filled with tunneling electrons. So a ray of light, and it's all virtual particles anyway, which makes it very hard to explain. Also, so there's you've got a ray of light going through space from one point in the background to another point in the background to another point to another point, and so on. It's a different photon each time, it's a different electron each time. We know this via the principle of non-locality that was given a Nobel Prize back in 2022, I think it was, and or 2021 or something like that. So yeah, there's this non-local realism that pervades reality, and the electrons, they're not in the same location all the time. There's for every time it absorbs a photon, it tunnels somewhere else in the universe, gets replaced by a different electron with almost the same energy photon in it, releases that photon, and then that photon travels through space for a little while, gets absorbed by an electron again, that electron tunnels to somewhere else in space, a new electron takes that electron's place, and so on and so forth. And he said at the beginning of his comment that I hadn't mathematically worked all this out. I grant you I haven't fully mathematically worked it all out, but it does have some mathematical support, my ideas. It'd be nice if you sort of read the papers on it, but there we go. The idea of gravitons is very mainstream. I know that already, thank you. In the low energy approximation, spin 2 gravitons will replace Einstein's tensor field equations exactly. Okay, but Lesage's model cannot reproduce relativistic effects of GR. In fact, it strictly violates the equivalence principle because of gravitational shielding. There is invariance because of aberration, and it does not account for gravitation interacting with mass energy rather than just mass density. There's a... Yeah, okay, right, Lesage gravity, I just included that as a sort of a pedagogical aid to understanding my idea, because my idea is a kind of a quantum ether theory. Lesage gravity, that's from the 18th century, it's from the 17th and 18th centuries when de Deuillet and Lesage were working on that idea. I'm not proposing that exactly. I'm proposing something that it has its basis in those ideas, certainly. That's the jumping off point for the theory. But I'm by no means saying that Lesage gravity is the truth. I'm not talking about any of these electric universe theories either, where it's flows of electrons, and at least they have the idea of electrons being the particle of gravity in EU theory. That's something that can be said for that. But it's not classical flows of electrons around stars and planets causing gravitational fields to exist. Most certainly not. It's something, as I've described, that they exist in space for a tiny period of time, then absorb a photon, disappear to somewhere else via the uncertainty principle, which causes them to relocate to a different location in the universe. Then another electron pops up to take its place. This is non-locality. That's non-local realism for you. It makes it very, very hard to explain. And really, I was just invoking Lesage gravity and ether theories and all these sorts of things to make it fucking easier for people to understand, rather than going off and talking about non-local realism straight at the outset and baffling half my audience. Sorry about that, but that's just what I was trying to do there. There's a phenomenon of drag. There's not. Hang on, that was a bit before that. No, I wasn't. There's the phenomenon of drag that is not clear that it will predict what you say, and it requires the force-carrying particle to travel faster than c. The force-carrying particles do travel faster than light. That's one of the strangest things that quantum mechanics has discovered, and it's a hard and fast discovery, I'm afraid to say. Electrons don't tunnel at the speed of light. There is no gap at all in terms of time between an electron appearing in one place, and we know, by the way, that quantum tunneling exists. We know that electrons don't stay in the same position, and they're jumping around all over the place constantly, and they do so faster than light. They do so instantaneously, not at the speed of light. It's one of the major reasons why there's an inconsistency there between quantum mechanics and general relativity. Relativity predicting that everything must travel at the speed of light, whereas quantum mechanics says clearly that isn't the case. So yeah, that's my objection to that bit of the paragraph. In any case, Lethargy's model is very different to the sort of thing you seem to be proposing. At least you acknowledge that. Thank you very much. You're right that electrons interact with light. I know I am. This would make a cloud of them surrounding massive objects radiate massively. We don't see this. Like, this is the worst bit of this comment. I'm sorry to say it. We do see it. We definitely see that. Like, haven't you seen the images of black holes recently? That radiate massively. Well, they certainly trap huge amounts of radiation surrounding the event horizons of black holes. We absolutely see that. We see that even around the sun. We see that the radiation, like that in the corona of the sun, that radiates a huge amount of energy. The corona is really, really, really hot. And by the corona, I mean like the atmosphere of the sun, or the shroud of gravity particles that surround the sun, in my best understanding of what this amounts to. That traps a huge amount of radiation around the sun's photosphere. The sun's photosphere, the surface of the sun, is only about 5,700 Kelvin. It's surprisingly cool. But yeah, no, we do see that, definitely. We have an abundance of evidence that black holes radiate huge amounts of energy, tons and tons and tons of it, all via Hawking radiation. So again, by the way, thinking in terms of the gravitational electrons as virtual particles, just to exclude this non-local realism bit from the explanation, just to make this a little easier to understand, say that they are a stable cloud of particles instead of appearing and disappearing around the universe all the time and so on. Like an electron jumps out of the cloud of electrons surrounding the black hole into the event horizon, picks up a photon, jumps out again, and deposits the photon there. And that's what we call Hawking radiation. And if you look into something called causal dynamical triangulation, which is one of the mainstream approaches to quantum gravity at the moment, it was a collaboration, I think, at the University of Delft, who's been working on this, or they've come up with this thing that I suggested a few years ago, that all objects emit Hawking radiation. So they don't emit loads and loads of radiation by any stretch of the imagination. It's not obvious on Earth. It would be a little bit more obvious with the sun, and certainly very obvious with black holes. But all objects emit Hawking radiation. That's one of the things that causal dynamical triangulations research groups have come up with. So that wouldn't expect to see they'd be radiating massively. We don't see this. We do. Our best science indicates that this would make a cloud of the surrounding massive objects radiate massively. We don't see this. We do see it. Sorry to say. Yeah, we have the theory of Hawking radiation. We need to apply that to all things in the universe, though, which, I mean, is where our best understanding, I think, of quantum gravity is probably headed. Far from explaining gravity, you would require, contrary to observation, some gravity-like force much stronger than electromagnetism to overcome this repulsion, which would also make this redundant as a theory of gravitation. I don't know what you're talking about there. I really don't. Far from explaining gravity, you would require, contrary to observation, some gravity-like force much stronger than electromagnetism to overcome this repulsion, which would also make this redundant as a theory of gravitation. Well, I'm suggesting a unification between electromagnetism and gravity, and stating pretty unambiguously, I think that gravitation is just a symptom of electromagnetism, or vice versa. But I don't know what you're talking about there. Also, bodies which accumulated negative charges would repel each other, not attract! Exclamation mark. Which accumulated negative charges. I'm not talking about them accumulating negative charges at all. I think that's a subtlety on which you're slipping up there very much. Like, I'm not talking about an object that's positively charged. Well, okay, say I'm talking about an object that's positively charged. Say a proton in the nucleus of an atom, and we'll take it like this. So you've got the proton in the nucleus of a hydrogen atom. It accumulates one negative charge. It accumulates the electron that goes, not like that, but goes around the orbits the nucleus of a hydrogen atom. It can hold one negative charge. It can't hold more than that. If it were to be able to hold more negative charges for whatever reason, well, it would be a different atom, wouldn't it? We would just call it something different. We would call it like nitrogen or oxygen or uranium or something like that, if it could hold more than one negative charge. But yeah, we don't see that. I don't see the relevance of that. I'm not talking about magic here. I'm not talking about something that could hold. Also, bodies which accumulated. You've completely misunderstood what I'm saying. I'm sorry to say that I've baffled you on this level, but even if some bodies had positive and others negative charge, I'm not saying that at all, and I've never said that. So the idea is somehow to treat gravitation as an instance of Coulomb's law. You do not get gravitational behavior. I'm saying that you can apply Coulomb, and this is how I've worked it out mathematically, by applying Coulomb's law to gravitating systems, to quantum gravitating systems, such as two hydrogen atoms in a box at a Lagrange point. So like this, that's what I've done. I'm not saying it's an instance of Coulomb's law where you have classical charges interacting, and that's the usual zone in which you would use Coulomb's law. I get it. You do not get gravitational behavior, where you get forces of attraction, don't you, between charges? So that's similar to gravitation, at least, and it might explain the gravitation. That's sort of the point of it. In fact, the usual phenomenon of electromagnetism in that case would come into effect, so you would get complicated magnetic interactions which would behave very ungravitationally. Or like magnetic hydrodynamics of magnetic fields, I guess, surrounding suns and Earths, and these flows of photon fluid, I guess, is what you would call it, in a kind of a quantum field theoretic sense, when it comes to magnetic hydrodynamics and gravitational fields and magnetic fields and so on. But yeah, I'm saying that in a sort of unification model, all that sort of does have to go together, and we certainly have to have gravito-electromagnetic behaviour. And gravito-electromagnetism, as I understand it, that is mainstream physics. That's an outgrowth of general relativity, or something general relativity had to account for. And general relativity itself is also a theory of electromagnetism, let's not forget. It's also about the propagation of light waves through space. It is also about, these phenomena of magnetism and electrostatic force. Well, it fails to go that far, I think, but it builds on special relativity, which is about the propagation of light waves through space, which is electromagnetic behavior, and that is included in general relativity. So general relativity, to some extent, is also a theory of electromagnetism. But what does it say again? In fact, the usual phenomena of electromagnetism in that case would come into effect, so that you would get complicated magnetic interactions which would behave very ungravitationally. Yeah, I mean, you've committed there at the very last the essential error of, which is common, I think, among people who are new to physics, of believing that gravity and electromagnetism are separate interactions. They're not separate interactions at all, and no one in physics actually treats them as being separate or separable. Since, as I said, special relativity is can be seen as a condensation of Maxwell's laws of electromagnetism, and general relativity grew out of special relativity. So you get a gravito-electromagnetic interaction, I suppose, or a theory of gravito-electromagnetism via general relativity and special relativity, if you see what I mean. However, clearly, general relativity doesn't go far enough, because there's remaining problems in general relativity, such as the problems of dark energy and dark matter, these two huge holes in the sciences. So, in aid of patching those sciences up, we can gather clues from here, there, and everywhere about how it really works and about how gravitational fields really work. And if you think about it just at the surface level, why doesn't the Earth, for instance, spin infinitely fast? Why doesn't it travel around the sun at the speed of light? But, well, you know, because is there nothing to slow it down? On the one hand, we travel around the sun because, well, we're trapped in the sun's gravitational field, and I think we orbit it more or less at the same sort of rate that the sun rotates. I'm not butchering that so much, which I probably am. Or we rotate in tandem with the sun's rotation. So the sun rotates, the Earth is trapped in its gravitational field, and the Earth rotates, I guess, however quickly that part of the gravitational field rotates. But yeah, I mean, there's still resistance in the background. That's the other thing to sort of try and realise, I think. There's still quite clearly stuff in the background slowing down the Earth's rotation from some very high speed. For example, I mean, if there were nothing at all in the background, like nothing at all, the idea of nothing at all, complete nothingness, a total and perfect vacuum, which, I mean, isn't a very scientific idea in the slightest, since we don't observe anything like that in nature ever. There's always a background in nature, which is why I disagree with things like background independence in quantum theory. But if we were to conjecture that the background is a perfect vacuum, and that there's no form of resistance whatever in the background, then surely the Earth would spin infinitely fast with an arbitrarily small amount of momentum given to its rotation. Do you see what I mean by that? Whereas it clearly doesn't spin infinitely quickly, it doesn't move through space infinitely fast. So on the one hand, yes, it's being carried around by an attractive force, or really it's being kept in place by an attractive force. But the other side of that coin is that there's a repulsive force which is preventing it from going to incredibly high or stupidly high speeds like infinity. And we see resistance there in the background all over the place. We see it notably in the rotation curves of galaxies. This is where dark matter comes into things. We see it notably where stars rotate at the extremities of galaxies rather fast, whereas towards the centre they're sluggish, they're slowed down by some sort of energy field in the background, or some, what I would say, particle field, some field of material objects with negative charges slowing them down from infinity, or slowing them down, to a lower speed than what they'd have at the extremities of galaxies. So I think I've covered that. Yeah, a lot of effort went into that comment, but I'm sorry to say, you've totally misunderstood what I'm saying. And you haven't seen, why haven't you looked at an image of a black hole through a telescope? Through a radio telescope, which is what we have now. Because, you can see the gravitational fields, they've been emitting huge amounts of radiation. Yes, you are right. But yes, we do observe that. So I'm sorry to say, you need to go away and learn more physics. That's just the end of it.